All right, so last time we were in the middle of working through some Venn diagrams. We'd done this particular example, which had two different sets that we were combining, and we combined with a union operation. The one we're going to look at today to start with is going to combine three sets. So we're going to take the set A, and we're going to do the intersection with the set B. That's inside of a set of parentheses. And then we're going to do the union of that with set C. This starts out very much like we did the last time. We're going to start by drawing a rectangle. The difference is that our rectangle is actually going to have how many circles this time? 3 circles. So I need to draw a circle here in my rectangle. And this circle, I'm going to use a property, some of you have seen me do this before, but not everybody. I'm going to clone this. It's like copy and pasting it. It makes a second one that I can move. And then I can clone it again to make a third one that I can move. So this is what those 3 overlapping circles would look like. You could label them in any order. It really wouldn't matter. If you're just trying to sort of make sure that yours matches mine so that our numbers and everything turn out, I've got mine labeled A, B, C. And then the union out here is like, not the union, the universal set, excuse me, is labeled U. So we have more than 4 regions on this picture, right? Yeah. We've got lots of overlapping pieces and pieces that don't overlap. There's lots of different regions. In fact, there's 8 of them. The number on the outside, I'm going to start in the very top corner. The number here I'm going to put as the number 1 that's outside of circle A. This piece of overlap between A and B I'm going to call 2. And over here, the B only part I'm going to call 3. And then I'm going to come down here to these middle overlapping pieces. I'm going to call this 4. 5 in the very middle and 6. I'm going to put 7 down here in the bottom for part C, and then 8 on the outside. If you choose to do your numbers in a different order, it's fine. It's not going to hurt anything. We'll have the same shading at the end. Our numbers just won't match at the end because they'll be representing different pieces of the graph. So is everybody to the point where you've got numbers written in all pieces? And does everybody understand that I expect to see numbers when you do a problem like this in your homework or your test? Okay, good. All right, so we're going to do the process the same way we did on part A. It's just that we've got more process to do because I've got more sets to combine. The first thing you notice is that you're sort of have parentheses, and just like parentheses with addition and subtraction and other things, we do what happens inside the parentheses first. So the first piece inside the parentheses includes sets A and B. So I need to list out the values, the number of values that I've located inside of circle A. So what numbers are included inside of circle A? 1, 2, 4, and 5. What numbers are included inside of circle B? 2, 3, 5, and 6. Is everybody good so far? Okay, so that's the individual pieces. And then inside this parenthesis, it says I'm going to combine them, and I'm going to combine them with the symbol that looks like this. What does that symbol mean? That is the intersection symbol. So as I'm doing this, I need to find the intersection. And what does intersection mean of sets? What they have in common. Right? What do they both have in them? Where do they overlap? So looking at those sets of numbers, what do they both have in them in common? 2 and 5. So the first piece that I just did is I did the combination of A intersect B, and I found out that that is 2, 5. I'm not done, but I'm halfway done, right? I've done half of this sort of description up here. It may look like 2/3, but it's really not. It's really half of it. Because I'm supposed to take the result of that, which is the 2 and the 5, and I'm supposed to do the union with set C. So the next thing I'm going to do is I'm going to list out here C below this. And I'm going to list all the things that are in circle C. So what are in circle C? 4, 5, 6, and 7. And now I'm supposed to do the union. What does union mean? Combining them, and I get everything, right? I get everything when I do the union. Again, remember it's what we talked about in terms of the union of the marriage, right? When you get married, you get it all. You get the good, you get the bad. So if I'm going to combine it, I'm going to get everything. What values am I going to list here? 2, 4, 5, 6, and 7. We don't to list the 5 twice. That would just be redundant. That's silly. So we don't list it twice. But it was in both original sets. What do I still need to do? Shade. So I need to shade the graph that represents these 5 pieces. So I need to shade inside of circle 2, or region 2, region 4, region 5, region 6, and region 7. And that is the part of the graph that represents A intersect B union C. Any questions on that one?
When you're shading, does it need to look like separate shading?
No, no. I was just doing a piece at a time, so no, it can actually look like they're above. Don't make me guess though if something's shaded. Make it very clear if it's supposed to be shaded or if it's not. I understand sometimes we need to do erasures and things like that, but I don't want to have to guess if you meant to shade something or not. It should actually match the numbers you've written down, so there shouldn't be any question. Okay. All right, we're going to do one more. This one's a little bit more complicated. I'm going to do A intersect B complement intersect C complement. Okay, so somebody lead me through. What am I going to do first? Draw a diagram. So I need a rectangle, right, Audrey? What needs to go inside my rectangle? 3 circles, right? Now what? Gotta label them. So I'm going to do it in the same order that I did last time. And it'll look like that. Good first steps. Now what? We need some numbers in there. I'm going to number them the same way I did last time. And then I'm actually ready to do some work, right? I mean, so far this is just the setup, and it looks the same every time for 3 sets. What's different every time for 3 sets is actually the problem that I'm working. So I'm starting this problem with set A and set B complement. Why am I not writing down C complement yet? I need to do the stuff in parentheses first. Exactly right, Taylor. All right, so what is inside of circle A? And 1, right? Did you say 1?
Yeah.
Okay, sorry, I didn't do that one. Yeah. Okay, 1, 2, 4, and 5. Good. Then it says B complement, which means what am I looking for? Outside of B. So I need to know the numbers that are outside of circle B. And so what would that be? Excellent. I'm going to combine these with what set operation? Intersection. This says intersection right here. So I need to do A intersect B complement, which means what am I looking for among the set of lists? Things they have in common, which would be the number 1 and the number 4. Perfect. So this one is 1 and 4. We're half done. What else do I need to do? Find C complement. What is C complement going to be? 1, 2, 3, and 8. And I'm supposed to combine those with what operation? Intersection again, which means I'm looking for what they have in common, which is 1. So the answer to this question in a numerical form is the number 1. And the last thing to do then is to shade in region 1. Good? All right. There's one other type of diagram we're going to take a look at that can make use of the diagrams, or one type of problem that can make use of the Venn diagrams. This is an appropriate Venn diagram when we've got actual numbers that mean values, or numbers of people instead of categories. So I'm actually going to give you a list of data. That's where we're going to start with on this one. And I don't know why I haven't updated this slide to just include this already for you, but we'll just have fun and write it down together. So this is N of A is 24. N of B, also 24. N of C is 26. N of A intersect B is 10. N of B intersect C is 8. And N of A intersect C is 15. N of A intersect B intersect C is 6. And the last one is N of U is 15. After you get those jotted down, the picture starts out like the other pictures did. Rectangle with 3 circles.
What's that last one say?
N of U. And the U we mean there is not U for union, it's U for universal set. It's the U that I keep writing on the outside of these pictures. Like that. You guys ready to start filling in details? These work different. I don't just put numbers 1 through 8 on this diagram. That's not what's going on because I'm not trying to shade anything or anything like that. What I've actually been given is I've given values that represent different numbers of people or items in these different categories. It actually represents the number of things. And that's why it says N of A. It means the number of items in set A. The problem with N of A being 24 is that N of A would actually represent everything inside of this circle A. And this circle A has this outer region of A, it has the overlap with B, it has the overlap with C, and it has the overlap with A and C, with B and C. There's 4 different regions inside of circle A. And we really don't want to just do a guess, put some numbers in, and try and see if it works out. Because we could guess a lot of different things, right? It would not be a terribly efficient, guessing check's not a terribly efficient problem-solving strategy for this, right? But if you take a look one line down from that, where it tells you N of A intersect B is 10, you're getting better chances of being able to work with this. A intersect B would be this overlapping piece right here. But there's still 2 places where we can have numbers that have to add up to 10. So again, that's still giving me lots of options, right? I can do 10 and 0, I can do 1 and 9, and 5 and 5, and 4 and 6. You have lots of pictures, right, that I can make of that. But there is one piece of information here that is very specific. It tells me exactly where to put a number. Do you know which one it is? You got it, Amber. It's this one right here. That piece of information actually tells me where 3 circles all overlap. Right? That's the very center picture. It's the number where the place where we were putting the number 5 before. It's the very center picture of our diagram. So this actually tells me that it's the number 6 that goes right there. And what we're going to do then is that now that I know there's that number 6 there, if you go just one line above where I was talking about before, we actually don't have any more choices. This says that A intersect B is 10. Well, 6 of them are already here, so how many goes in this place? 4. And we can do the same thing with the next piece of information, so I'll just underline them as I put them in there. B intersects C. Well, here's circle B on the right, and here's circle C on the bottom. B intersect C includes the 6 that's here and this piece right here, and those have to add up to the number 8. So how many go in this outer place where they're intersecting? 2. And the last intersection that we're told about is A intersects C, which is over here on the right, this football shape on the right. I've got the 6 already, it's got to add to 15, so what goes in the missing piece? 9. Is that pretty good so far? So we've got all the overlapping pieces. That's really good, because now if you take a look at circle A, which originally had 4 unknown values, how many unknown values are there in circle A now? There's only 1, right? This outer piece right here is the only thing that I don't have a number written in. So it's supposed to be 24. How many do I have represented here so far? I have a 9, a 6, and a 4. How many is that? That's 19. I'm supposed to have 24, so Brenda, how many's left? 5. So there's a 5 left over here in order for that circle to hold. In total, add up to 24. Same thing over here with circle B. I can look at this. It's also supposed to actually add up to 24. I've got the region that's got the 4, the 6, and the 2. That's a total of 12. How many is left to go inside of circle B? 12. All right, circle C down here at the bottom. It's supposed to add up to 26. Well, I already done that one too. It's supposed to add up to 26. How many is here so far? 9 and 6 and 2 is 17. And I'm supposed to have 26. So how many is missing? 9. It's not a very good 9. There's one location where I don't have a number yet. Where is it? It's on the outside. Now, this piece of information is the only piece that's left. N of u equals 50. You know what that's telling you? Very good. Everything inside the box, including the circles, have to add up to 50. So grab your calculator. I want you to add up all the numbers that are inside the circle. So we have 5, 4, 12, 9, 6, 2, and 9. How many do I have? How many? 47. Okay, so there's 47 inside my circle, which means how many am I missing? 3. So there must be 3 on the outside of the circle. So the whole idea behind this particular kind of a diagram is to find a location, and it is often the center of the picture. It's not always, but it's often the center of the picture, where you actually know one of these very specific regions and sort of just work your way out from there. Okay? Well, let's do one where you can see this being used in context. It's a little simpler. It doesn't have 3 circles. All right. Joe Long works on albums for musicians. Last year he worked on 12 projects. He wrote and produced 2. He wrote 5. He produced 7. How many projects did he write and not produce, produce and not write, neither write nor produce? So there's 2 different things Joe does. What does he do in this description? He writes or produces. So when I'm drawing my picture, I've got this rectangle, and how many circles do I need to have in it? 2. Okay. And you can label them exactly what they are. This is write, this is produce. So there's no ambiguity about what's going on. You can call this universal set U outside. Okay, so it says he wrote and produced 2, wrote 5, produced 7. Where in the world does this leave us as where we need to begin? Which pieces of these 3 pieces of information is the one we want to start with?
Wrote and produced.
Yes. This right here, the fact that he wrote and produced, where is that located, Taylor?
The center.
That's the center. And the key word actually there's the word and. And is the same as intersection. It means and, where they have both in common. And. So that number right there was the number 2 goes inside here. Very good. Now we can actually do either of the other 2 to start with. It doesn't really matter. This one says he wrote 5. So this right circle has to add up to 5, which means how many more do I need? 3. So we've done that one. And then I've got one that says he produces 7. So this whole circle over here for produce is supposed to add up to 7. So I need 5. I still need one more number on the outside. How am I going to find that number? The 12. This 12 up here at the top tells us about how many projects he worked on. Right? It says he worked on 12. How many projects are currently represented in this picture? 10. So how many projects go on the outside? 2. Because the whole circle's, whole diagram, the whole rectangle is supposed to add up to 12. Using that diagram now, we can answer the following questions. So if you did happen to make a mistake on the diagram, I would love to see that your answers match your diagram, because you're not getting sort of double whammy. But we do want to answer based on the diagram that we have to work with. So let's take a look at the first one. It says, how many projects did he write and not produce? That's 3. Right, that's the outside of the right circle. How many did he produce but not write? 5. And how many did he neither write nor produce? 2. The questions are generally very easy to work and to find after you've done the diagram. The diagram is the part where it's difficult. All good? got one more. This one, loads of fun. Lots going on. I said one more, I meant one more of these. It says, a youth group is asked questions regarding songs they learned as children. Upon surveying 34 youth, the following results were obtained. 15 learned Jesus Loved Me, 8 This Little Light of Mine, 28 the B-I-B-L-E, 13 both Jesus Loves Me and the B-I-B-L-E, 15 both This Little Light of Mine and the B-I-B-L-E, and then 14 both This Little Light of Mine and Jesus Loves Me. 13 knew all three of them, and then we've got questions that were asked. So starting with a rectangle with how many circles inside? How many? 3, right? Whoa. Okay, what are the circles that I have inside going to be? The songs. I'll just go in order of how they were first given. So this first one over here is going to be Jesus Loves Me. I'll just write Jesus, so it won't have the name in there. The second one was This Little Light of Mine. How would I write light? And then the third one was the B-I-B-L-E, which I'll write on the bottom. And this is the universal set you on the outside. All right, got a lot of information. Which piece is the piece I should start with? The last one. This one says 13 had learned all three. So where does this piece of information go? In the very center, there's 13. Mark them off as I go. Okay, I think I can actually just go up from there, right? It says 14 had learned This Little Light of Mine and Jesus Loves Me. So in my picture, that piece of information is actually above my 13, right? So the number above the 13 plus the 13 have to add up to 14. So how many more do I need above the 13? 1. All right, light and Bible is on the right-hand side over here. It's supposed to add up to a total of 15. I've already got 13, which means the number out here is 2. And then this one says 13 had learned Jesus Loves Me in the Bible. That's this right side over here. What's going to go in this piece? 0 is going to go here, because I've already got all 13 people represented, right? From the center. So this piece does not get anything. It's got a 0 in it. Perfectly legitimate to have a 0 there. All right, I said has. This should say had. Typo, my goodness. 28 had learned the B-I-B-L-E. All right, so 28 is supposed to be the whole B-I-B-L-E circle. How many are currently in the B-I-B-L-E circle? 15, and I'm supposed to have 28, which means I'm missing 13 people down here. 18 had learned This Little Light of Mine. Where is that? Over here, right? So I've got 13, I've got 2, I've got 1 for a total of 16, and there's supposed to be 18, which means I'm missing 2. 2 on the outside. Good. The next one says 15 had learned Jesus Loves Me. I already have 13, 1, and 0 of those accounted for, which means I need 1 more on the outside circle. And I'm missing 1 number on the very outside. How am I going to find it? Using the 34 as the number of youth that were surveyed. How many are in my picture? 32? So I'm only missing 2 kids. So we'll put 2 kids out here. All right, so we're going to answer these questions then. These questions are a little bit more complicated than the last question. You're going to be seeing some questions that use these kind of phrases, so I want to make sure you saw it here first. Exactly one of these songs. What in the world is that talking about? The ones that are the circles that are the circles on the outside, right? So which numbers am I looking at if I'm looking at this one? This 1, this 2, and this 13. Those are the exactly one songs. 1 plus 2 plus 13 is a total of 16. Now when you're doing this on your paper, it will probably help me to be able to award partial credit in case you make a mistake. If you actually write out the numbers that you intended to be adding, and then tell me that the answer is 16. That way, in case you do make a simple arithmetic error, or you just left one of them out, I can give you some partial credit for having done so. All right, what about the second one? At least two of these songs. So where in the world in the picture is the at least two part? Okay, so the 1, the 0, where else? The 2, and the 13. The phrase says at least, which means this number or more. So 2 or more is the same thing as at least in this case. So we include the 1, the 0, the 2, and the 13 for a total of what? 16, and none of them were the same as the first 16, were they? But happen to be the same number on this particular one. How many have learned none of these songs? 2, that's the number here on the outside, right? And how many have learned This Little Light of Mine but no others? That's 2. Again, same answer, but for a different part of the picture from the outside, This Little Light of Mine. Did you guys see how to work with this kind of a diagram? How to use it? Okay, I think we have one more slide. Alright, we'll go in order. It says, is the operation of the Cartesian product commutative? Why or why not? We did the Cartesian product last time. Let me go back up to that slide just to remind you what that one was. There it is. Alright, Cartesian product. So the Cartesian product is the process of making ordered pairs out of elements from two different sets, and you combine them like this. Okay, that was the Cartesian product. Your question that you're looking at, I'll leave this slide up until we answer it, asks, is the operation commutative? Do you know what commutative means? Some of you have taken that too. We talked about here as well. Do you guys remember? So commutative means you can change the order. So like when we say 5 times 2 is equal to 2 times 5, that's the commutative property. It says the order of the multiplication doesn't matter. So in order for this question to be answered correctly, or to be the answer yes, our question is whether or not the order here means the same thing. Would the 0.13 be the same as the 0.31? No, it wouldn't in general, right? And hopefully you're thinking about, because I'm kind of hinting at it, the XY plane when you're thinking about this. Those are two different locations in space in XY plane, right? These are not the same. So the answer is no. And I'll say it this way. We can consider the XY plane and these two ordered pairs are different points. They're not the same points. They don't represent the same location. Okay, so that's interesting because we actually did talk about the operation of doing a union or an intersection, and those were commutative. We could switch the order around. It didn't matter. A intersect B is going to B intersect A. So what this is actually telling us is that if I do the Cartesian product, it would be different if I did it the other way around. So that does not have an equal sign between them. The other question to talk about on this one, sort of a conceptual question, is the student argues that adding two sets and taking the union of two sets is the same thing. How do you respond? So let's start with, what in the world is a union? What do we do when we find a union of two sets? So you combine them together and you take everything, right? So we sort of, we were doing those with the arguments with the pictures or whatever, we were just listing out all of the elements that were in both sets, right? Or whatever. So that's the union. What is adding two sets? What you described as intersection. Yeah, what they have in common is intersection of two sets. What is adding of two sets?
Combining all of them together.
That sounds like union, right? But you might. The problem is we don't really know because we don't have an operation of addition of sets, do we? I mean, I didn't show you one anyway, right? You've not seen one. And that's kind of the problem is that, you know, even as you asked Audrey, you said, well, would it be this? Didn't you? Like, well, maybe it's that. You did it too, Taylor, when you said, well, maybe it's this. Because you're sort of guessing because you don't really have a definition of what it looks like to talk about in an addition of two sets. So the first issue is that addition on sets is not an operation. We do not have an operation called addition on sets. It's kind of like, right, when we were talking about arithmetic, you don't have an operation with arithmetic with union. What in the world does 1 union 2 mean? It's not an operation on numbers, right? It's an operation on sets, but it's not an operation on numbers. It doesn't mean anything. Same thing with this. There is not an operation called addition on sets. However, it is true that there's an addition relationship, and we talked about this equation before, that if you wanted to find the number of items in A union B, that would be the number of items in the first set plus the number of items in the second set. Unfortunately, then we would have to subtract off the intersection because we double count. Do you guys remember that double counting last time? I drew a picture about the double counting. So there is a relationship between addition and union. But notice this is not a relationship between addition of sets. These items are all numbers. When we put that n in front of something like that, we're talking about the number of items in the set, not the actual items in the set. I don't add my family and my sister's family. We could add the number of people in both of our families, but we don't add the families. It doesn't even sort of make sense, right? So you can talk about the union, that's marriage in terms of families, where you combine families in that way. But you don't just add families. Same thing with sets. We don't add sets. It's just not an operation that we use. Okay? All right. Go ahead and write down the homework if you don't have that one listed yet.